edition of the new Astronomy of Public Talk series, which are talks given by our graduate students at a public level. The primary audience, there's several groups of people we want to reach. First of all, anybody who's interested, but specifically first semester experienced students, FSE students need to come to these sorts of things now and then, and this is something we're offering for them. We also want it just to be open to the community in general, bring friends, bring family. I'm glad this time the room is big enough. I was afraid it would be too small. That's a joke. But I do hope that we have several times this many people come to these talks in the future. So the first speaker is Dept. He's a grad student here at UMKC. He works with Professor McIntosh on galaxy evolution topics, and today he's going to talk about galaxies. Take it away.
Thank you, Mohan. Wait for it. Thank you. Okay, so I'm going to talk about galaxies, menagerie of galaxies. But let's first understand what the heck menagerie means, because I didn't know 3 days ago. Thanks to Mark. So I googled and it showed collection of wild animals kept in captivity for exhibition. Didn't feel like the right word to use. Googled a bit more and it said strange diverse collection of things. Makes sense. This is a picture of galaxy cluster in which all kinds of galaxies are there with different shapes and colors, so we can call it a menagerie. So here we have menagerie of galaxies. So let's move on and see what all we learn. Okay, so in this huge population of our audience, I'm going to ask questions a few times, and feel free to raise your hand. So here is a collage of few galaxies. How many of you have seen at least one of these galaxies or similar to this galaxy? Cool. So seems like it's a very popular one. Okay, so can you say what are these galaxies called, which are question marked? Does anyone know? Yeah?
Spiral.
Yep, spiral galaxy. So clearly here we can see that in this collage, two distinct populations just based on the shape you can see. So first are spirals. They look bluish in color, and that is because of they are also actively forming stars. That is very by actively forming stars we mean that new stars are forming there, and all those new stars are young and white or blue. That's why they look bluish. And our Milky Way is a spiral galaxy. Of course we are in it, so we cannot see it full. And this is a picture from Chile, from where we have got this like full arc of one of the galactic arcs of our galaxy. And on a clear night sky, you can definitely see like this. This is through a DSLR camera, but even through your iPhone and all, you can very clearly, distinctly see a huge patch of density in the sky, on a very dark sky, and it will look like this thing, galactic arc. And then, what are these galaxies? Does anyone know what do we call them?
Spheroid?
Yeah, thanks, Brandon.
Yeah.
I know you know. Yep, they are spheroidal or elliptical galaxies. They are reddish in color, and they are not forming any new stars. They are dead, usually dead for a long time, and all the old stars are usually in their dying phase look yellowish and reddish. So this galaxy looks overall reddish. But in the present universe, most of the population of galaxies that we have are either spiral or ellipticals, but that's not the whole picture. We have irregular galaxies too. We call them irregular because they don't have any distinct shape. Yes, sorry. Yeah. They have distinct shape, so no distinct shape, and often they are results of collision or mergers of two galaxies or more. So all these are going through some merger. And so there is a simulation. Let's see that. People tried simulation of merging two galaxies, and does it match with the observation? Those are real ones, and through simulation we can see this. this one, right? Looks like this one. Yes. So yeah, even through simulation, we can predict how when two galaxies merge at different phases, how they're going to look like. Okay, now we understand. We saw three different distinct populations of galaxies: ellipticals, ellipticals or spheroidals, spirals, irregulars, and now there are these galaxies which definitely look like a very distinct shape, but yeah, those are also there, not as populous as the spirals or ellipticals, but they are also there too, and we call them ring galaxies because they look like rings. And usually they are a result of when smaller galaxy rams to the center of a larger galaxy, it forms a ring due to the shock wave of the collision, and usually the collision has to be head on and at a perfect angle, then only you get ring-like structure. Then we have another one, jellyfish galaxies. We are so good at naming astronomers. So it looks like jellyfish, so like tentacles of jellyfish, so we call them jellyfish galaxies. They are usually spiral galaxies falling into the galaxy cluster, and as they are falling in, hot gas of galaxy clusters strip out the cold gas or gas of these spiral galaxies, and they look like as tentacles. And here is a 3D visualization, a simulation of a spiral galaxy falling into a galaxy cluster and becoming a jellyfish. At this point, the gases are being stripped out because they are falling into the galaxy cluster, which is a very dense medium. Now, a little aside from the talk, since I mentioned the term galaxy cluster, so I thought, okay, let's discuss a bit about galaxy cluster, what they are. So we saw a picture of a galaxy, simple. If a galaxy is isolated, it will just one galaxy. Usually the size of spiral or any typical normal galaxy like ours is between the size of 0.01 to 0.1 megaparsec. And galaxy groups are groups of galaxies in a confined space or in a given volume. Usually less than 100 if they are together, we call them galaxy groups. But in the same amount of space as a galaxy group, if you have 1000 galaxies, then we call them galaxy cluster. Number density of galaxies in a very small volume is so huge compared to galaxy group, and their size is around the size of galaxy group or even more. Max it goes around 10 megaparsec. So now that, and again in the previous one I mentioned the new term megaparsec. So what is megaparsec? Now let's understand that. It's a unit of distance in our field because usually things are so far that we just cannot express in miles or kilometers. So we have to find some bigger units. This another video might help. Let me our galaxy, Milky Way. So if and what is 1 light year? Light 1 light year is distance traveled by light in 1 year, and light travels with the speed of 186,100,000 miles per second. I get confused in miles, 3 lakh kilometers per second. So if light travel, so what does 3 million light year mean? That means the distance traveled by light in 3 million years, and that much distance is 1 megaparsec. And the whole size of our galaxy is just 100,000 light years. So in terms of megaparsec, it's very, very small, just 0.03 megaparsec. And so just 0.03 megaparsec. And so Milky Way in terms of megaparsec, we can say it's 0.03 megaparsec size. A galaxy group will be 33 Milky Way aligned in a line. That shows a galaxy group will be. A galaxy cluster, 33 or 10 times bigger than that, multiple galaxy groups together. So these are huge, huge things. Another aside, it will be the last one. So before moving on forward, let's discuss a bit about electromagnetic spectrum. So far, all the galaxies that you have seen are through optical telescopes. That is, like the telescopes which are in Hawaii, Keck Telescopes, or the Hubble Space Telescope, which is in space. So if our eyes would have been that bigger and in those locations, we would have seen the same picture. But the light coming from space comes in all the wavelengths. So light can be classified, like it has energy emits in all different wavelengths, and it goes from higher energy or shorter wavelength gamma to longer wavelength or lesser energy, that is radio. So all the light came that is in visible spectrum, this very small window. We saw all those images of galaxies when we saw through this small window. But other window that reaches, other light that reaches Earth is radio one. So next we'll look at galaxies, how they look like if you see in the radio regime, and that's why I wanted to introduce a bit of what exactly electromagnetic spectrum is. Usually in our field, we study any source in the sky almost in all the wavelengths to get a complete picture, to understand the thing. Once you see all the wavelength, you can say more about its properties. Some things are just specific to one particular wavelength, some properties, so it becomes important. And only optical and radio we can get light on Earth. For rest all we have to go in space to observe. So all the telescopes are usually in space. And this is just for a comparison, like a gamma ray shorter wavelength of what size, a radio wave microwave are of what size, just the size wavelength of the wave. Okay, then with this aside, now next is, so far whatever galaxies you saw, spiral looked normal, elliptical also looked familiar, irregular was a new, ring, all those I guess new for all of you. So now even more crazy kind of galaxies you're gonna see. First one is galaxies that work at radio wavelengths, focus on work part, and the next is galaxies seen at radio wavelengths. These work at radio wavelengths. Okay, these are the actual galaxies which work at radio wavelengths, which we image them at radio wavelengths. So, how many of you have seen galaxies like this in popular picture? No astro students. Those are my colleagues. Yeah, so it appears that hardly when you talk about galaxies, the image usually comes in common, like non-astro people would be spiral galaxies. But then these are other things that our eye doesn't see or our optical telescope doesn't see. And each of them are unique in their own way, and we have classified them in different namings. Largely FR2s, FR1, GRGs, head tail and X shape, and one by one we will discuss what are these galaxies or why they look like that. So let's discuss FR1 and FR2 first. It was discovered by or identified by Fanaroff and Riley, two astronomers. Fanaroff is South African and Riley British. During his PhD, Fanaroff collaborated with Riley and they identified these galaxies and they named on this name. So FR is Fanaroff Riley 1, Fanaroff Riley 2, and all the radio galaxies they observed at that time they classified mostly in these two categories. And if an FR1 is something, a radio galaxy which has two-sided jets and is brightest closer to the core and has no distinct combination of jets. Like if you had very sensitive telescope and observe for longer time, the wave, these final emissions, these diffuse emissions will keep on going for longer, even larger size. So usually they are of the size of 0.3 megaparsec, which is equal to 10 Milky Way galaxies aligned in a straight line. And FR2 are usually a bit shorter than the FR1s, and they are usually the length of 3 Milky Way galaxies. They often have seen as one-sided jets. Doesn't mean that it has one-sided, it has two-sided. It's because of one particular, I'm not using jargon for other colleagues. Because of the relativistic beaming, other side we are not able to see, or in normal terms I can say because of Doppler effect, other side wave subject at the other side is moving away from us, and because of Doppler effect, the intensity or the brightness of that the wave reaching us will be very less, and that's why we are not able to pick that part. But it does have jets both sides, but often seen one-sided, and their edge is often brightened and has lobes, and they have distinct combination. Wherever these bright spots are, they terminate at that point, and we call them hot spots. And often they are more luminous, or in simple terms, they are more bright than the FR1s. So largely they have classified like this, these two kinds of galaxies, or most of radio galaxies. Then another one was head-tail galaxies. So head-tail galaxy looks like it has a head and tail, so we call them head-tail. So they are also of size of usually 0.3 megaparsec, that is 10 Milky Ways, and often having two-sided jets. And as they move through the gas between the galaxies, or as they are falling in the galaxy cluster, those jets get blown back, just like this, how the ear of this dog is blowing back because of the wind. So, and usually they are brightest at the closer to the core, and they also do not have any distinct combination of jets like how FR2 had. Next are X-shaped galaxies. Of course, they look X-shaped, so we call them X-shaped. But then they changed the name and they are calling it double boomerang-shaped galaxy. So they tried explaining why they are looking like X-shaped. The earlier explanation was that maybe, so we'll see it in the coming slides, that something common is there in all of these galaxies. And that common thing is a supermassive black hole is at the center, and from which jets are coming out. So people thought that okay, maybe the black hole changed its orientation. So one time jet was like this, after some time jets went in another direction, and so we have X shape. But further study revealed that that's not what is happening. Actually, jets are turned back. So first time if the jet was moving this direction and this direction, then after a while it started turning back, and the high density gas here or high pressure gas here reflected it to the other side, and so it started looking like an X shape. And these are usually this one. I haven't seen any other. I guess there are multiple X-shaped galaxies, but a very few. I couldn't find a picture of other one, but this one was the size of 1.6 megaparsec, which is huge and 50 times the size of the Milky Way. So as you're progressing forward in this radio galaxies, we are saying that FR2 was 0.1 megaparsec, FR2 was 0.3. Now we have reached to 1.6 megaparsec. So these are very, very big galaxies. Imagine just one single galaxy is equivalent to 50 times of our own galaxy, which itself is huge. Then there are these giant radio galaxies. As the name suggests, they are really, really giant. And this was just discovered like 3 weeks or 2 weeks ago. And this is the giant in the giants, the largest one we have seen so far. So these two are an example of typical giant radio galaxy. When the size is larger than 0.7 megaparsec, then we call them giant radio galaxy. That X shape can also be called as GRGs, but it has a distinct X shape, so we call them X shape. But yeah, GRGs are so huge. This thing is 5 megaparsec, which is equivalent to 170 Milky Ways in a straight line. And this is the largest galaxy we have observed so far. But we don't understand yet how the jets have become so big. So that's an open question. Whoever wants to do research, that's one topic. And yeah, another one is 75 times the Milky Way, that long. And a galaxy cluster that we discussed, which contains thousands of galaxies together. In this image, that will be typically of this size, and in this image, that it will be half of this one, like somewhere around this. So these are much bigger than the galaxy cluster, which itself contains 1,000 galaxies. Oh, somehow I added animation. Okay. So the common thing in all of these galaxies was that there is a supermassive black hole at the center, and around which some matter charged particles or dust and everything are accreting and gradually falling into the black hole. And this is just an artist's impression that how it looks like usually, that there is supermassive black hole at the center, there is things to eat around it, and those are falling inside it, and then black hole often overeats and then vomits as jets. So let's watch a video which tells about a bit of AGN. We call them active galactic nuclei because they are at the nucleus of the galaxy, and they are active, that means they are actively eating and belching and vomiting. So this video.
Looking up on a clear night, you can
okay, let's do 1.5.
see stars spread across the sky in all directions, unless you're in the city, in which case you're lucky to see the stars at all. But if you're fortunate enough to be in a dark place away from the city lights, you might even see the band of the Milky Way stretching from one horizon to the other. This is the disk of our own galaxy, where the concentration of stars is so dense that it appears as a milky band of light, since our eyes can't distinguish the individual stars. But what we see with our eyes is only a small part. Our eyes can only detect light in the visible part of the electromagnetic spectrum. What would the sky look like if our eyes could see radio waves or X-rays? Galaxies are not just made up of stars. They also contain a lot of gas and dust, and, at the heart of all large galaxies, a supermassive black hole, millions or even billions of times the mass of our Sun, squeezed down into a space smaller than our solar system. Although very small compared with the scale of an entire galaxy, these black holes can have a huge impact on the galaxy's growth and formation. In cases where there is a lot of gas in the central regions of the galaxy, this material can be accreted onto the black hole via an accretion disk, releasing a lot of energy in the process. This is what we call an active galactic nucleus, or AGN. The radiation produced by the AGN is so bright that it can outshine the entire galaxy, producing far more energy than all of the galaxy's stars combined. This accretion process can also form huge jets of strong magnetic fields emanating out from around the black hole, and fast-moving electrons spiraling around these magnetic fields produce huge quantities of radio emissions. These radio jets can grow to enormous sizes, sometimes extending far beyond the galaxy to be millions of light years across. They can also provide information on the past activity of the central black hole, similar to how different layers of rock and sediment in the Earth's surface can provide insight into past geological environments. Different epochs of accretion activity are marked out in the structure of the radio jets. However, not all galaxies have AGN, and not all AGN produce radio jets. In fact, only about 10% of active galactic nuclei produce radio jets. Discovering what causes an active nucleus and why only some of them have huge jets is one of the key unanswered questions about galaxy formation. Studying these galaxies in different parts of the electromagnetic spectrum gives us complementary information about different parts of the active galactic nucleus. For example, the radiation from the accretion disk is brightest at optical and ultraviolet wavelengths, while infrared radiation comes from the dusty regions that surround the black hole. The jets produce a lot of radio emissions, and hot gas surrounding the central black hole region can produce X-ray emissions. And to fully understand the physics at play in these galaxies, we need to piece all this information together to get the complete picture of AGN.
Okay, I hope that added some extra info than what I added. Now, done learning about galaxies. Of course, there are other kinds of galaxies too, but I guess I didn't have time to add other kinds of too. We call them quasars, blazars, and many others. There's tons of different kinds of galaxies. But broadly, most of the 80% kinds of galaxies we have covered in this slide. Now let's discuss about astronomy at UMKC here. So I'll discuss a bit about Galaxy Evolution Group. We call our group as Galaxy Evolution Group. What are the research area, team members and members research, what course we offer. Then we have a telescope here in the campus itself, we call it Marco Observatory, and how to get involved with us, and then some astros learning. So in our group we have two professors, Professor Brodwin and Professor McIntosh. Brodwin is, I call him Mark. Brodwin, she is here, so I call him Mark. So he's an observational cosmologist, and Dan, my supervisor, our PhD supervisor, he's a galaxy demographer. So Dan usually studies changes in galaxy population over cosmic time, and Mark studies evolution of massive galaxy clusters over cosmic time, that is a few billion years, which is again hard to comprehend. And in Mark's team, he has 3 PhD students, all 3 of them are here, Brandon, Ripon, and Ben. And in simple words, Brandon studies properties of galaxy cluster, Ripon studies detection of clusters, how to detect them, and then proto-superclusters, which is another thing that I didn't talk about superclusters. Superclusters are like how galaxy clusters are something huge, but they are still a gravitationally bound system, like falling at a one center gradually. But superclusters, they are probably 100 times the size of clusters usually, but they are not gravitationally bound. And proto-superclusters are basically the signatures of before a cluster is formed. Proto means the before part. So Ripon studies all this. For details, the students are here, you can ask them. And Ben studies Asian, these cool stuffs. And in Dan's team, my PhD supervisor, right now only I am there. These two recently graduated. He was a master's student, and we call him M. Kameshwara. He was a PhD student here, recently graduated, got a postdoc in University of Minnesota. So he used to study galaxy characterization. He had a bunch of galaxies and he would characterize them with different properties. And M used to study galaxy mergers. We saw the picture of galaxy merger earlier, or the simulations, those kind of things. And then I studied dead galaxies. dead galaxies were those elliptical galaxies, but mine are died very recently, and which is a puzzle because they live in such an environment that they should be alive, but they are dead. So my research is to find out the clues to explain why they are dead. So mine are recently dead. And then let's talk about the courses offered here. Usually at the level 300 level and up courses are cosmology taught by Mark, where we study large-scale structures of universe, or large-scale properties of universe, right from the Big Bang to now, in much detail, like how our universe came into existence, all those things. And then another course we offer is stellar astrophysics, which is taught by Dan, where we study physics of stars, how stars are formed and how they evolve and how they die. And another course is galaxies. So what we all studied here in much more comprehensive way, either Dan or Mark teach us this course. And then we have an astronomy research method course, which helps us become skilled to do professional research. So usually an undergrad, if they want to work with us, we prefer them if they have taken this course, then they have the skills to do various data analysis with us. And so this is a very important course which trains us to be professional researchers in our field. Then there is practical astronomy course, again taught by Mark. In that we usually learn about various types of telescopes and what all observation strategies we follow with different kinds of telescopes and their details. And then we have 100 and 200 level astronomy course, which are not as hard as these ones. Usually fun ones, and Mark teaches one particular course. What is it? Physics of sci-fi movies. What is that course?
Yeah, that's a 300 level course. It's fun.
Yeah.
It's science fiction.
So he usually in that rip apart the science of those science fiction movies. So Interstellar, Star Trek, Star Wars, all those movies, and we go in much detail that how absurd all those things are. Like, it's just theoretically not possible, and some are very intelligent in those movies. It's a fun course. So for courses, what all detail, always Mark and Dan are approachable. And then we also have in our University of Arco Observatory a telescope at the Royal Hall, at the terrace of the Royal Hall, and this is just opposite to Flagstone Hall. And most of us, except for the non-UMKC people, don't know where they are. And at the terrace we have two telescopes. One is 16-inch mirror, another is 14-inch. And observations we start usually from May to October. We do it around that time, and usually evening after 7 p.m. it's open. You can gather there, and it's a free pass for everyone. Often they post on their Facebook whether they are going to keep open the observatory or not. Sometimes due to bad weather they don't, so they post on Facebook. So this is one again for public use, like anyone can come, even non-UMKC people. It's for community too. Then how you can involve with us at UMKC? So we have a thing called Astro Hour. The typical time is Friday afternoon 1:30 p.m. for 1 hour. So whoever is interested in astronomy, they gather together every Friday. Traditionally, that was the time, every Friday. And like it's a very chill environment. Professors are there, Dan and Mark are there, but it's led by students. And whatever cool happened in our field, any exciting news in past 1 week, we discuss all those things, or sometimes even some academic issues or some important academic thing we have to deal with. Those also we are open to discuss, but mainly astronomy we discuss there. And chill environment, so students bring their food, they eat there, they discuss, and Mark and Dan usually facilitate the discussion. Like if sometimes students are not able to understand something, they will help us what exactly the thing are. And it's a fun setup, and it's open for community too. Usually we do in our conference room, which is very small, just like I think maximum it can accommodate 20 people. But if more and more interest we are having from community as well as students, then we can always switch to big rooms, no issue with that, but it's open for both. Then we have journal club, and we are thinking of renaming things, renaming it, we're thinking of calling it Astro Meetup or something. It's run by one of the colleagues, mine, Ben, fellow PhD student. In that, the idea is to undergrads, grads meet together for 1 hour every week. It's a get-together time, but still discuss each other's research, or even if undergrad has some doubt that they feel shy to ask to professors, they can ask to grad students. And again, chill place, bring food, eat and discuss, no problem. Idea is to eventually, like it's like a mixer event. We mix up with undergrads so much that they feel comfortable in approaching us, and then together we can discuss some cool papers that come out every week or every day in astronomy. So usually right now it's once in 2 weeks we meet on Thursdays at 3, right? So if the students have this kind of impression that everyone has to bring some paper already prepared and then talk about that in a meeting, then no, it's not like that. It's a very stress-free meeting. Even if you have no paper prepared, we can always open some paper there and together we can tear that paper apart. Or always can discuss about how it's like to be a PhD student in our field, or how it feels like to be a researcher, how to apply for PhD programs or IU programs, to have summer internship, research internship at different universities. So we have gone through all those, all the grad students, so we can help and easily talk, and usually professors don't have time for all this. So this is like for undergrads and grads to use us as a resource and also mix with us. And then we have GEG meeting, which is meeting between professors and their grad students, their PhD students and grad students are all, and undergrads are also welcome who are doing undergrad with astrophysics interests. And this is a bit high level discussion where we discuss our research on in every 2 weeks, and it's very much not at all at public or popular level, like how you saw the talk today. It's very comprehensive, so that's why it's not open for community. But again, it's Dan's or Mark's call whether it will ever be open for community or not. Then we have astronomy public level talks, which we started today itself. This is inaugural, and hoping this will attract students and the community here in KC. And then summer internships and year-round projects with PhD students or professors is also possible. In summer, some students, some undergrads work with me, not just UMKC, Rockhurst. So one of my students from Rockhurst is here, he worked with me. And even if you are beyond summer time, throughout the year, some project, some collaboration you can always do with PhD students or professors. We always have tons of work. So, and that's an opportunity for you to learn and feel how it feels like to do research in astronomy, and see if you are really interested to do such kind of stuff. And then we have this Bridge to Stars programs for high school KC students. This, I'm not sure if just for high school. So far it looks like just for high school, but I also feel like it can be provided to some KC community members, some old folks who had that, who want to again come back to astronomy, but not at very hard 300 level courses, but at very basic level. I feel like those people also can do this course. So it was developed by my supervisor Dan, and he talks about what exactly this program is, and nice that some of the KC community members are here who knows this might attract them, and they would want their kids to be in this program. So let's listen to this.
I have to go to the YouTube version to get this.
Astronomy is awe-inspiring and causes lots of curiosity for us because it's about what is out there in the universe and where do we come from, and it touches on questions about our origins. And I think that's what inspires people, and makes it a very attractive class for students to learn about science. A Bridge to the Stars scholarship program is a unique and exciting opportunity for Kansas City high school students to take an introductory astronomy course at UMKC for college credit. They get to take this class with me, a professional astrophysicist, and learn all about the universe around them. So I offer 2 intro astronomy classes. The first one, Astro 150, is called Motions of the Cosmos. And in that class, students learn all about the many different motions, how everything is moving in the universe. They learn about gravity, which causes most motions. They learn about the expansion of the universe. They learn about the birth of planets. They learn about what stars leave behind when they die. They learn about the connection between galaxies and dark matter. The second class, Astro 155, is called Starlight and Star Stuff. In that class, students learn how astronomers decipher the cosmic message in starlight. They learn how light interacts with the stuff that the universe is made out of, atoms. They learn about the birth and death of stars. They learn how stars change during their lives. They learn about planets orbiting other stars, which we call exoplanets, the possibility of life in the universe. They learn about the Big Bang and what astronomers think might be the end of the universe. Because students are very active in my courses, meaning they have many opportunities to discuss ideas with their peers, they gain an excellent understanding of the concepts. This means they really learn about astronomy and about the universe. There are many benefits to taking these courses. Besides gaining a real conceptual understanding of how things work, Bridge scholars in the program have undergrad mentors, UMKC students, that help to assure that they have success in their course. And finally, at the end of the semester, they get to meet with me and get advice on how to pursue a STEM degree. Astronomy offers a wonderful gateway or bridge to careers in science, technology, engineering, or math. So interested students can find out about a Bridge to the Stars scholarship by going to our webpage. Extra information plus all the application forms are found here.
So next is, even if you're not in UMKC, still you can do various free astro research. One thing is this data-driven astronomy course. So this is course taught by University of Sydney, and in that you learn about a particular kind of stars, we get called pulsars, it's called. So how to understand the data we take from the telescope and then figure out what the data is saying. All about that is learned in this course. It costs, but it's also free if you don't want the degree from University of Sydney. So we really don't need all this degree, you can just do it for free. And then there is this, several citizen science projects are there, usually on this website Universe. So one of the project is Characterizing Galaxies. You have a bunch of galaxies and then you classify them in different names. FR1, FR2, this and that. So it looks like the website. Anyway, you don't have to see the website. Then there is another one, Getting Started with Data Analysis, where again this is all free. They'll teach you how to do data analysis for different kinds of stars, data for different stars, and how to figure out the properties of stars. All those are free. Again on Universe, there is this telescope through which there was a survey to find exoplanets. So this citizen science project, in which if you get involved, you'll find them hunt planets using this data from this survey. And then there is this another Facebook page. It's called Rad at Home, where you do actual very professional research in astronomy. On Facebook, there is this huge telescope in India, radio telescope, called Jmrt, Giant Meter Wave Radio Telescope. And often, of all the radio telescopes, whatever data has been observed, usually 60% is unused data and it's in archive. And so this telescope has so much unused data. So this case, the leader of this Facebook page, Professor Ananda Ota, who is an astronomer, he trains the students on Facebook to how to use their data to do some research using that data and teaches some of the skills that is necessary to do various kinds of analysis. And anyone who is on Facebook can just contact him and go through the very structured process he has and get the feel of doing actual research in radio astronomy. Then this universe website itself, it has so many of citizen science projects, not just in astronomy but various other fields. So you can collaborate and contribute like that in different kind of projects. And then there is this thing called CASA tutorials. So there are top class radio telescopes in the world, ALMA, VLA, VI, ATCA. So telescope itself is a different talk. Maybe one of us can give talks on telescopes someday. So data observed by these telescopes, how to analyze the radio data. Those are just numbers, how to make sense of those numbers. Here they have free tutorials for all these telescopes, and it doesn't really require much prerequisite knowledge. You can follow step by step to get a feel how it feels like to analyze the radio data. So all these are free resources available to do research in astronomy and learn the skills. And for this, one doesn't have to go to any university. And yeah, all the references that I used are here. I will finally thank you. Leave with this collage. So now let's open for Q&A.
Yeah, thanks, Dio. We want to open up here the last few minutes for questions.
So let's switch on the light.
Maybe like that. Questions on anything that you presented to us today, or just anything else that you find interesting in astronomy. We have a few grad students in the room, and we can answer most questions you might have. So, go ahead.
So I got a question about was it the radio? Could you pull up the radio galaxy? Forward a few slides.
Like forward.
Yeah, toward the
This one?
no. Okay, so those jets coming out of the black hole, is that radio? Is that mostly radio waves?
Yeah.
Okay, then can you go one more, I think?
Backward or forward?
Forward.
Looking up on a clear night, you can see stars spread across the sky in all directions, unless you're in them.
Yeah, I think after that is.
There was one that was showing kind of blob-like features at the end of the jets. Well, yeah, one like
This one? It's
like that FR2.
R2 at the bottom.
This one?
The big one in the middle.
This
Yeah,
one?
that one.
Oh,
Is that radio waves
Yeah, yeah.
we're looking at?
Yeah.
The pink is radio
Yeah,
waves?
pink is radio, center is optical. So the galaxy from which it is coming out, the wave, the galaxy is, if you see through the optical telescope, it's just this much.
So are the radio waves interacting with some cloud-like matter, and that's what's being reflected back to us as these kind of billowy loads?
Right. So you feel like some brightness here, right? So those jets are sometimes it's not very continuous, and depending on how much black hole is getting food, it has an accretion disk around it, right? So at times, let's say it ate so much and it doesn't have much of food around it. So jets might stop for a bit, but then if once it gets full again, it will again shoot the jet. So that's why you have these distinct looking like feature, but it usually there's nothing is around it. Usually they're in very isolated space, unless they're in clusters. So these radio jets, they do interact through the medium between the cluster or within the cluster, but usually space is very empty, so it's not like it's hitting other galaxies or anything.
Well, so something had, I mean, those are actual photos of,
Yeah.
of so something had to reflect it back our way, right? Because it was just
Oh.
going down.
Okay, you are thinking since it's not in our direction, how we are seeing it.
Yeah, yeah.
Okay. No, I think usually light is coming in all directions spherically, and we are, so something will definitely come to our direction too, and we are seeing that part. Other side part, you can see it, usually it's everywhere, the light is spherically
So
coming.
think of it like someone's pointing a laser and it's just going in that direction. Think about it as a series of candles that are shining in all directions. So even if it's not coming right at you, if you're looking from the side, you're seeing light from the sun. It's light is being emitted in all directions.
So is it energy or gas? Like what you're seeing in the pink like spheres?
So these are charged particles which are
Yeah, I mean,
ejected out
the
through the magnetic field of the black hole itself. So these are particles, small charged particles. So we wish you can call them bunch of charged particles, I don't know, gas or dust.
The black hole is emitting powerful radiation in all directions, but it's sitting in a galaxy, and so the radiation sort of it can only escape perpendicular to the disk, and so it shoots out in a jet like this. It's also got very powerful magnetic fields because the disk is spinning, and the particles are all ionized. That is, there's no neutral particles. The electrons are ripped off of all the atoms, and so everything's charged. And this disk is spinning, and the accretion disk is spinning, and it's winding up the magnetic fields, and it creates a situation where the charges are forced up the magnetic field, and they're forced to travel away out of the galaxy along these magnetic fields. And since they're accelerating, anything that's going in a circle is accelerating, is changing its direction. Anything that's accelerating is going to emit radiation. So those electrons themselves that are being forced out are emitting radiation in the radio. And that's what we see there. And they emit the radiation basically in all directions because they're moving in all directions.
So you can call it energy in radio.
Yeah, the jets are mechanical. It's a way that we can actually mechanically move material from like near the accretion disk way far out from the galaxy. These like the electrons, the gas that was around the accretion disk is no longer breathing down to the galaxy. It is no longer.
When he says mechanical, it means it's not just light shining, it's particles coming. It's a part of the galaxy being forced out into space.
So it's part of this radio waves.
And the radio waves are being emitted by the material that is out there. Did you have a question also? But yeah, that's a good question. That's one of the harder things to understand. Is actually
Like we really don't know.
it's not a fully solved problem by any stretch. It's way too complicated for physics to do. We know how to do it in principle, but there's no computer strong enough to do it. It would take forever to do a full hydromagnetic simulation. So it's very complicated physics to figure out exactly what's happening near a black hole. But it's very high energy, and we have the outlines of the answer. You can solve a problem to various levels of precision. And, we go far enough that we can handle the calculation. We know on what range of scales and sizes and energies that the calculation is valid, and it does explain the features to us. And further, simulations can reproduce a lot of these features of black holes, but not all the details. That's too complicated. Any questions about anything in astronomy? Yeah?
Can FR1s turn into FR2s?
That's a good question. I don't know.
You're the radio expert too.
Well, I think it depends in what environment they are. The reason they are FR2 is because the jets that is coming out in the environment, most likely here the environment is more dense compared to the environment these people got, and so they didn't have any obstruction to their jet. Here they got some obstruction due to the higher, denser medium in which their jet was going, and they couldn't move further, and they started just bouncing there itself and started making low blind structure. So it's about the media, environment we are in. So if somehow something happens that FR1 lands up in an environment similar to like these higher dense environment, maybe can turn. For example, I don't know if one irregular galaxy is falling in a cluster, like started falling and experiencing the higher density environment, may experience something, or this might become something like this. FR1 will become like this.
In that top right one, the two arms look kind of symmetrical. They seem to have the same shape. Is that just by coincidence, or is there something there causing that?
The jets coming out from the black hole is symmetric, and because the magnetic field, both side, opposite direction is same, and same magnetic field will give out the same force on the jet, and that's why it's symmetric. But then also if the environment here in one is almost very same, then you will see symmetry. If somehow the environment here is more dense to here, then there will be a difference. So it's usually most of them look symmetric because they are very much isolated, alone, no one is around them. Oh, sorry.
Yes, I was wondering, like, okay, so what specifically are you referring to when you say that a galaxy is dead? Because with the elliptical galaxies, you're saying that they're long dead, but they're still emitting optical light. So, like, what specifically are you referring to when you say that a galaxy has died?
So these are elliptical galaxies. So by that we mean no new stars are being formed. So to form stars we need hydrogen gas. So what happened in these galaxies? All the hydrogen gas has been used up in forming stars. So all the stars have been already formed, no more gas, so no more new stars, so we call them dead. So that's, and so stars will be still there, just that all the stars are old stars, and you're getting light from the old stars.
Yeah, so just to recap, on this side of the room, the answer of why are these galaxies dead is they have no star formation. No new star formation is going on. The fact that they still show light is not surprising. The old stars that are left here actually are going to live for billions and billions. They're going to live longer by a factor of several than the universe has been in existence. Their lifetime, the old stars, is 100 billion years or more. The universe is only 14 billion. So it's going to be there for a long time. So a dead galaxy doesn't mean no light, it just means no new stars. Yeah?
What classes is UMKC going to be offered in the upcoming fall semester?
In the fall semester, what was the dance course this past fall? I think it's stellar. So this fall, the galaxies course has been announced. That course requires.
Last semester we did that.
You said it was
I was in that.
So this coming fall, it's going to be STARS, the Stellar Structure course, that Professor McIntosh teaches. That course is at the 300 level, so it requires that you've done sort of the 200 level physics and calculus courses and stuff like that to take that. And in the spring, I'm going to be teaching the 400 level cosmology course, which is definitely a higher level course.
Can you explain a bit what we learn in cosmology?
So cosmology is the study of the whole universe as a structure. So instead of thinking about how a galaxy evolves or changes, we think about how the universe evolves and changes as a whole. And so this starts from the Big Bang, and it goes through many of the early phases of the universe's evolution. There's the Big Bang. There's a phase called inflation, where the universe gets we have inflation now in the economy, but this is a different inflation where the universe gets really big really fast, and then that phase stops and the universe evolves in a normal way, and it covers how all the matter comes to be. Where was all the hydrogen created? Where was the helium? Where was the lithium? Where was the carbon? There's different answers for all of those. So we talk about what those are. We talk ultimately about the formation of galaxies and also just the evolution of the universe as a dynamic structure. How big is it growing versus time? If you want to talk about the radius, the size of the universe versus time, how is that changing and why? What does it depend on? And if we understand that, can we predict not just what happened, can we like understand what happened in the past, but can we predict what's going to happen in the future? Is the universe going to end up expanding forever? Is it going to collapse back down in another sort of big crunch? Or as it looks like is the case right now, is it going to not just expand, but have the expansion accelerate so fast for time that ultimately all the other galaxies we see in the sky are going to recede from us eventually faster than the speed of light, so we won't see them anymore. And in 100 billion years, our night sky, our nearby neighbor Andromeda is going to merge with us. And in 100 billion years, if current models are correct, the universe is going to be gone from our night sky. We're not going to see any other galaxies, just our galaxy. Not even going to see the cosmic microwave background, because it too will, not be, the light from it will not be able to reach us. And it'll be a very weird place, but that's 100 billion years. The point is to understand, based just on the simple, it's not simple, but based on the fundamental physics that we could in principle write down on one blackboard, the entire history and future of the universe. So that's a big task to take on. I don't know, you took it. Did it work?
I like the course.
So that's what's going to be offered next spring. At the lower levels, this fall I'm probably teaching one of the 100 level courses called Life Beyond Earth, where we focus on the prospects for life elsewhere in our solar system and ultimately life around planets, on planets around other stars, and how we would find those planets and stuff like that. So that should be offered this fall again. I'm not sure what else is offered, but if you are interested, just shoot me an email and sit down and chat about the options.
Yeah, the community members can definitely easily reach out to any of the grad students or professors through the website, and they are very easily approachable.
Okay, I think we're past it. So any other questions?
You have one question?
Well, I don't want to go over time.
No,
I had questions about the dust in the galaxies. So, is there generally more dust than there is the hydrogen that makes up the stars, or is it more or less?
I would say hydrogen is more because the reason is all stars are forming, and then even all the hydrogen, most of them are not used, and still hydrogen is there, and often it is in different form, either ionized form or in molecular form. So they are like if you start with, okay, there are in a galaxy usually there is supermassive black hole, there are stars, there is gas, there is dust. These are the major contents of the galaxy. So total mass of stars contribute more to the overall mass of galaxy. Then comes gas, and usually hydrogen and helium, and then probably dust. So gas will go.
And does the dust come from exploding stars, or where does the dust come from?
Yeah, exploding stars.
You can see dust in that galaxy at the top.
Yeah.
Dark stars.
So stars first, and the dust comes from them.
Yeah. Star formation creates everything. That's sort of the answer to the question I said before. Where are things made? Outside hydrogen and helium, almost everything else around us is made in stars, either during their normal lives or in their deaths. And that's a process of fusion where you build heavier elements and lighter ones. When the star finally explodes, there's a few ways stars meet their demise. But however that happens, all the stuff they've created throughout its lifetime is seeded out to the galaxy around it, and the next generation of stars is made from that gas. So the next generation of stars typically has more what we call metals, things heavier than helium, more metals in it than the earlier generation. But not all of it ends up trapped in a new star. A lot of it just ends up loose in the galaxy.
Because it just seems like there's a lot of clumping in the dust. So
Yeah, well, it's really good at blocking light in the optical dust, as you can see. And in the infrared, that dust itself is emissive because the dust is heated up by the radiation hitting it from the hot stars. And when you heat something up, it glows, right? And so it actually glows in the infrared. If we looked at a far infrared view, we would see that dust would not be dark, it would be light, actually. The rest of the galaxy would disappear. Because it finds stuff glowing at around, tens of degrees Kelvin, 30, 40 degrees above absolute zero. That's where the dust, that's its temperature. It glows like an object that has that temperature. It looks like a lot, but Theo's right, it's a small, in fact, he said it exactly right. The biggest component of a galaxy is dark matter. The next biggest is the stellar mass, which is typically 10 times less mass. And then 10 times less than that is the gas mass, and 10 times less than that is the dust mass. So the dust mass is pretty big. Okay, great. Well, thanks, Theo, again.
No, that didn't give me so I had no idea. I don't know how many students are there.